Hi, everyone, and welcome to our Peabody Science Cafe about the study of life on other planets. My name is Sydney, and I'm going to be moderating today's conversation. Welcome, we're excited to have you here. So we have two wonderful speakers with us tonight, and I'm going to introduce them in just a second. But first, to tell you a little bit about the format. We're going to start off with just some introductions and a little bit of background about the work that both of our guests do. But we hope to spend most of our time answering audience questions. So at any point tonight, if you have a question, feel free to submit it through the Q&A function. We're not going to be looking at the chat, and we're not going to be calling on people to speak. So please just submit your questions through the Q&A. They can be for one or both of our speakers, and we're going to get to as many of them as possible. So to jump right in, our first guest tonight is Dr. Debra Fischer, who is the Eugene Higgins Professor of Astronomy and a professor in the Department of Statistics and Data Science and Earth and Planetary Sciences. We also have with us Dr. Lisa Messeri, who is an assistant professor of anthropology. So Lisa and Deborah, if you want to join me. Welcome.
Hi, thanks for having us.
Thanks for being here. So to get started, we'd love to just hear a little bit more about you and your work. Deborah, do you want to start us off?
Sure, be happy to. So the topic tonight is the search for life on other planets. And I would say that right now our focus is just on finding those other planets. In particular, I'm interested in finding planets similar to the Earth. We understand a little bit about how life got started here on Earth, as you may have heard a couple of weeks ago. And so the question now is, can we find a sort of Earth 2.0? The first exoplanet, that's a planet orbiting another star, was detected in 1995 by Michel Mayor and Didier Queloz, who recently won the Nobel Prize for their pioneering work. And I joined as an exoplanet with a group in California with Jeff Marcy and Paul Butler in 1997. And one of the things that I noticed is if you look at the rate of planet detection as a function of time, it's clear that after I started, the field really took off because the number of exoplanets since I became engaged in the field has really become exponentially grown. At that time, the big question really was, do other stars have planets? And there was a lot of debate among astronomers about whether that was the case. I remember my colleague, Dimitar Saselov at Harvard University, sort of fondly said, Deborah, most other stars probably don't have planets. And that's because stars form in clusters, and the most massive stars are short-lived. They'll go supernova, and they'll photoionize and blow away the protoplanetary disks around other stars. And what that probably means is that our sun was a star on the outer regions of the cluster. So that was a perfectly, reasonable hypothesis. But in fact, since that time, we've discovered so many exoplanets that we know that that scenario isn't right. We know that most stars form with planets. In the early days, every exoplanet discovery was a press release. And most of those exoplanets that we were finding were big gas giant planets that had signals that were tens to hundreds of meters per second in size. So I became very interested at that time in whether or not we could use our radial velocity method for detecting planets to detect Earth analogs. And Earth, instead of inducing a signal of 10 to 100 meters per second, would only cause the star to move with a velocity or a speed of 10 centimeters per second. So it's a completely different game trying to find Earth analogs. And, my team just built the third spectrograph, and we are reaching that record-breaking instrumental precision. So there's been a lot of exciting progress on that front.
Thank you. That's a wonderful overview of your work in the field. Lisa, could you tell us a little bit about what you do and your understanding of the history of exoplanet research?
Sure. So I am a professor of anthropology, and my research is on the anthropology of science and technology. So I study all of the kind of non-technical aspects of science and technology, and I'm particularly interested in how science and technology shapes how we think about ourselves as humans. So how kind of these grand technological and scientific endeavors really tell us about what it means to be human and to be on Earth. So I wrote a book about exoplanet astronomy and planetary science that was published in 2016, which details, among others, the work of Debra Fischer and other planetary scientists and exoplanet astronomers. And I was drawn as an anthropologist to the field, particularly of exoplanet astronomy, because I was so fascinated with how these invisible planets became lively worlds. And I wanted to know how placemaking really affects and changes the kind of work that scientists do and how they see their work as mattering. So that's kind of what got me. I mean, I had a lifelong interest in astronomy, but as an anthropologist, I kind of came to the field through planetary science and through exoplanet astronomy. And I worked with scientists like Debra Fischer, who took me down to, or let me come with her down to CTIO, when I think that was that the second spectrograph that you guys had built for long shot? Oh, you're muted.
That's going to happen. I'm just trying to prevent my dogs from barking. No, that was the first spectrograph, Chiron, right? And Lisa was a graduate student, and it was so much fun to take her along on the observing run.
Yeah, so as an anthropologist, I was indulged with being able to sit there and kind of take notes while the scientists were themselves taking notes of other stars. So it's this, funny iterative process. And, so I did that research. I went down to CTIO with Deborah in 2010. And, the book that I wrote came out in 2016. And I've kind of, though I'm not in the thick of exoplanet astronomy as I was when I was doing my research and writing up, I've kind of maintained an interest and a fascination with the field and thinking about the history. So, Deborah just offered this really wonderful history of how in 1995, exoplanets were still potentially knowable and thought to be rare, and these kind of very exotic kinds of objects in the universe. And I was doing my field work right at the moment when the Kepler Space Telescope launched, and that was the first telescope that was dedicated to the search for exoplanets, with a particular hope of narrowing in on an Earth-like exoplanet. And that just made the numbers go from a couple hundred of exoplanets known to exist to the several thousand that we have today, and the understanding that the number is infinite, that there are infinite exoplanets. And what I have found really interesting, kind of from an anthropological perspective, about this very short history of exoplanet astronomy from the 1990s to today, and especially thinking about this question of life, is when I when I kind of came into the field as an outsider and as an observer, I was really taken with how geological the field was. That the way that exoplanets were talked about was in terms of the rockiness, the gaseousness, the dustiness, not even quite the wateriness. So very much about planets as these conglomerations of dust, rock, and ice. And it was a little bit verboten to talk about whether any of these exoplanets contained life or not. And something that has been really interesting in terms of the shift of the field and the history of the field is how, as the number of exoplanets have proliferated, and how the dogma has shifted from maybe no exoplanets or exoplanets as rare to exoplanets as abundant, there's been the ability for the question of life to come back into the field. And the way I think about it is this shift from exoplanet astronomy being kind of not motivated, but talked about with a geological imagination, to right now a shift towards letting back in the biological imagination in terms of understanding the science that's being done and why that science matters.
Thank you so much, Lisa. And I think that transitions perfectly into another sort of foundational question I have, which is, what are we looking for? So what does it mean to look for the potential for life or planets that could support life? You mentioned wateriness or rockiness or all these things. Maybe Deborah, can you say something about what it is that you're searching for, or what you think a life-supporting planet might be like?
Sure. Well, I think, first of all, astronomers define this region around stars, which they call the habitable zone. And I think it's more appropriately, it should be called the water zone. The idea is that if there is a planet that orbits at this distance from the star where it's not too hot and not too cold, that water might pool in a liquid form on the surface of that planet. And biologists tell us that wherever they find water on our planet, they also find life. So that association has always been with us. And we do realize as astronomers, we're not just being completely, self-centered and anthropogenic. We do realize that there could be gas giant planets in the habitable zone that have moons, which are perfectly lovely places for biology. But we've narrowed our definition in a sense for practical reasons. It's because the detection techniques that we use will tell us the mass or the size of the planet, and they will also tell us about the orbit. So how far away from the host star the planet resides. So with that information, making use of the information that we have, the concept of a habitable zone is actually rather useful. And I might just put down $100 right now that the first example of life that we will find will come from a planet that's not in the habitable zone.
Mm-hmm. That's so interesting. Lisa, in your experience, how has that concept of a habitable zone sort of developed, and how does it reflect, our own perspective when looking for life?
Yeah, I, as an anthropologist, when we hear a word like habitable zone or a phrase like habitable zone, we get very excited. Like, ooh, what does that mean? Like, what is this imagination of habitability? Where does it come from, et cetera? And so, I actually think that when I write about Deborah's work, I often write about it in conjunction with the concept of the habitable zone, and also what it means and the relationship between habitability and inhabitability, and what it means to inhabit and how that's different from simply the possibility of the existence of habitation. So habitable zone is actually this really fascinating concept that comes from like 19th century studies of the Earth. And originally the habitable zones were used to demarcate kind of altitudinal limits. So where on the peak of a mountain does life kind of cease to exist, or does vegetation cease to exist? So there were in that kind of 19th century imaginations, there were in fact places on Earth that were not habitable, were not suitably, inhabitable, and the assumption there is inhabitable by whom? Well, inhabited by humans. Mm-hmm. And so that kind of that term migrated in like the 80s or 90s into these kind of early understandings of how to think about the significance of all the different exoplanets that perhaps might be found. And so in that wielding of it, habitable zone very quickly became centered on this idea of the possible existence of water. And there's like just so many things I love about the concept of the habitable zone. First is how like snoozy that term is. Like habitable zone is such a clever way to conceal that actually what we're talking about are possibly aliens, right? I mean, like it's just such this like beautifully dull word that if as exoplanet astronomy needed to do in the beginning of the discipline, kind of maintain its like legitimacy, habitable zone was this perfect way to keep the excitement alive within the scientific community without necessarily overly promising to a broader public about what the science might offer. And I also love how habitable zone, I always think about it as like this pointer to life. So habitable zone, as Deborah just said, is all about the potential for the existence of liquid water on the surface. And liquid water is not yet itself life. It's, of course, yet another pointer to life. So habitable points to liquid water, which points to life. And so you get this really rich set of associations whenever or exoplanet astronomers begin talking about habitable zone. And it just, again, as from an anthropological perspective, it's such a rich concept that I just love learning more about and talking about.
That's so interesting. Yeah, I love the concept that we're sort of, right, we're putting our own human bias of what is habitability onto space. I mean, wow.
What else are we going to do, right?
Well, true. We actually have an audience question that's pretty related to this already, which is if we're now talking about the fact that exoplanets are common, is that because we are able to study so many more stars, or is it, and do we have a feeling of what percentage of stars have planets, or maybe have planets in a habitable zone? We're going to add that to it.
That's such a great question. Yeah, I think we've gone from 1995, where we would have said, if we're going to be serious scientists, let's just admit that we have no examples of other solar systems, that N, the number of stars with planetary systems, is equal to 1. But now, and in the early days of exoplanets using the radial velocity method, we were detecting these gas giant planets. But as Lisa said, the launch of the Kepler mission really gave us a sense of the statistics of exoplanets. And I think we've gone from thinking, maybe 0 stars have planetary systems, to thinking essentially 100% of stars have planetary systems. We don't find planets around 100% of the stars that we look at, but we also know that our observational techniques are limited, that we don't have the precision that we need yet to be able to detect the small worlds that are similar to the Earth, or planets that orbit at large distances from their host star. But from what we can see, we can make statistical inferences about what the underlying population looks like. And that number is going to be very high. I don't know if it's 90% or 97%. It's something that's high enough that it's essentially 100%.
Does that include binary or systems, or just single stars?
So actually, that's such a good question. So our sun is a single star, but sometimes stars exist in binary systems. So 2 stars will orbit each other. And our nearest neighbor, Alpha Centauri, is the perfect example, with not just 2 stars, Alpha Centauri A and Alpha Centauri B, but with a 3rd star, Proxima Centauri, which orbits much farther away around and sees Alpha Centauri A and B essentially as a single gravitational, well. So a triple star system is our nearest neighbor. And what we found with one of my postdocs, and so many people in this field have actually done research on whether or not binary stars can have exoplanets. And what we find is that, if the stars orbit each other with orbital periods of just days, we found planets that reside outside of that binary orbit, right? Which is incredible. And if the star separation is wider, then we find planets orbiting one or the other or both stars in a binary star system. So as long as the separation is relatively large, roughly 10 times the distance between the Earth and the Sun, the number of stars that have planets starts to go up. And they act almost like single stars.
That's amazing. Because that was not known when you were doing Project Longshot at CTIO.
I know, that's right.
Peer reviewers kept on telling you that it's not possible.
That's right. Yeah, this is a field where the theorists have essentially always been wrong. It's a field that's been really driven by observations, and my best friends who are theorists will admit that. So I'm not being rude to them behind their backs. They totally admit that. Yeah.
Well, that's so interesting. I sort of have a follow-up question to both of you then, which is, throughout the history of this field, have there been any big milestones that have either cast doubt on the potential for life or lended, sort of hope or evidence?
Do you want to start, Lisa?
I'm thinking about, there's been so many milestones, and like some of my favorite milestones are the milestone mistakes. When, like, for example, a lot of potentially habitable planets have been undiscovered. So I'm just trying to remember if I can get my exoplanet names right. Was it Gliese like 581b or something that was like this potentially habitable zone? This like really exciting discovery, potentially in the habitable zone, that like everyone was very excited about and got a press release and all this excitement. And then it was seen as like an error, right? Like, or no, it was G. It was 581G that was thought to be the habitable one in the system that then got.
Yes, that's right. That's right. That's right. Yes, exactly. Yeah, I mean, that happens because when we're looking at stars, the stars themselves aren't just like perfectly quiet, cooperative, un, objects without any, features themselves. The stars are these boiling cauldrons of hot plasma that have spots on them that rotate, and those, the surface of those stars have velocities of hundreds of meters per second. So it still astonishes me that we've been able to measure velocities of stars to 1 meter per second precision. That's our Doppler gun, like the cops on the highway, is aimed at the stars, and we can measure the motion of stars with that level of speed. And now with the latest generation of spectrographs, including the one that my team built, we're reaching 10 to 20 or 30 centimeters per second. So yeah, there have been some cases where we have been confused. And yeah, I think, astronomers are honest about that. And that's the great thing about science. You learn as a graduate student not to take it personally. It's not about you. It's about the ideas and finally getting things right. So yeah.
Yeah, but definitely the kind of the big discoveries in terms of like getting closer to this question of life on exoplanets are definitely the fanfare that come when planets are discovered in habitable zones. And
Right.
there's been a few of those discoveries around red dwarf stars or M dwarf stars. So not quite the sun-like stars, but stars for which the habitable zone is in a slightly different place that's like more easy to observe. Exactly. So we have these little like gateway planets that hopefully get us to the true Earth analog. And then there's like a few scattering of like biosignature papers, right? Where atmospheric readings have been taken and kind of the analysis of those.
I mean, that's amazing, right? These are planets that we don't even see, and yet astronomers are able to measure traces of atmospheric constituents in the exoplanets. I mean, it's just mind-boggling and incredibly exciting to me. Yeah, the landmarks, I would say in the early days, half of the field didn't believe that what we were finding were exoplanets. So the first confirmation of an exoplanet was when we found our technique predicted that if the system were being viewed edge on, that the planet would transit at exactly 7:42 p.m. And with that prediction, the photometry guys, were observing the brightness of the star, and at exactly the predicted moment saw the light from the star dim. And that measurement confirmed the size of the planet and really, taught us that, these objects really were planets. But I think Lisa's right that it's the planets that are in the so-called habitable zone that become really intriguing catches. So we're finding multi-planetary system architectures. We're finding planets around binary star systems. I mean, planets are just almost unavoidable. It's such a robust process. It's incredible.
Wow. Well, so to ask an audience question and add one more category to that, maybe someone's asking about the potential for life on Titan, Europa, or
Enceladus.
There we go.
All of these
what about within
places,
our solar system?
All of these great places that are not in the habitable zone.
Yeah.
Right. And that's exactly where we're looking in our solar system. And I would add Mars to that list as well. Mm-hmm. So, geez, I don't know. I kind of don't guess about these things, I guess. I think that these are important questions, that human beings are curious about their place in space and time and why we're here. And that answering these questions, finding life on one of these other bodies in the solar system will be amazing, because we'll be able to answer whether or not that life looks anything like the life on Earth. And therefore has a common origin, perhaps the same origin as our last common ancestor on Earth, or completely independent, right? Which would be even more amazing, because at that point, if we find life on Titan, which looks nothing like life on Earth, then I will go and tell all of my students, okay, guys, most of these planets that we're finding, many of these planets that we're finding are going to host life as well. So that's why the solar system searches are so important. And I don't know what my best bet is for any of this. I think we have to look and see.
Yeah, I mean, it goes back to a comment you made earlier, Deborah, about how, I mean, yeah, we are limited by what we know about life on Earth in terms of how we structure the scientific search for life elsewhere. But I think, again, that's like the real promise of the solar system searches is if we're going to be able to experiment with trying to detect like life otherwise, it has to be a bit closer because we have to be able to go and like poke at it in a way that we can't quite poke at, you know, even our closest exoplanet friends. So it's really complementary to think about it that way, that like it's going to be the solar system studies that if we're able to figure out what does it even mean to talk about life as we don't know it, like being able to do it closer to hand is going to hopefully have a little bit more success than
one super exciting thing to just point out is we've done an interesting study of the Earth. So we've had spacecraft look at the reflected light from the Earth on the moon or coming back to the Earth. Well, and we've asked the question, do we think from the spectrum of the Earth's atmosphere that there's life on the planet? And the answer is yes, that there's a combination of methane and oxygen and ozone in our atmosphere that wouldn't coexist, right? They wouldn't be in chemical equilibrium, would drive the methane out of the atmosphere. So we have biosignatures, signatures of life on our planet. And if we can't go and poke at them directly, as Lisa said, we're going to look at the atmospheres and see if we can find spectroscopic signatures of life.
Thank you. So we have I think, sort of related audience question that's very cool because I think it gets at both of your expertises sort of perfectly. So someone's asking, do we, or maybe should we, look for life on planets not in the habitable zone that are based on different chemistries or sort of different makeups than we see here on Earth? And basically they ask, given the range of environments represented in the universe, is it myopic or short-sighted to look for only life forms that resemble our own in only the kind of environments that we're observing here?
I once, like years and years ago, I saw a talk by the astrobiologist Chris McKay about you know, the current status of, I mean, astrobiology is where a lot more of this conversation happens, and exobiology. And so it was being asked about the current, and I think he got this exact same question from an audience member. Like, you know, aren't you being limited if you're looking for, you know, carbon-based life forms or water-dependent life forms? And he was very frank, and it was like, yes, but I don't know where else to start. Like, I kind of feel like we have to start somewhere, and that's where it is. So I definitely, like, my impression as an anthropologist, kind of talking with scientists who are passionate about finding life elsewhere, is that they desperately want to find these other kinds of life, but that is such a creative process, and it's hard. I mean, it's just creatively hard, it's scientifically hard, and it's probably, Deborah would be able to speak to this more, it would be probably very hard to robustly, you know, quote unquote, prove if like you're finding something that's quite otherwise. But it definitely seems like, I mean, given if we think, like, I don't know how far you can take the analog or the analogy rather of the diversity of kinds of exoplanets and kinds of planets, and the extent to which that might indicate a diversity of kinds of life, even at its most basic building blocks. Because if you were to take that analogy seriously, then there must be a proliferation of kinds of life that we don't even think to ask about. But I like watch with bated breath on the sidelines of what kind of experimentation would even get us to being able to ask the question of life otherwise.
Yeah. I mean, the perfect place to look for that life as we don't know it is Titan. where it's incredibly cold, and instead of liquid water, there are lakes of liquid methane, and it rains liquid ethane instead of, raindrops coming down. So it would be fascinating if we could find some alternative biochemistry there. The problem is, will we recognize it? And so there I would turn to the biochemists and ask them, if there was silicon-based life sitting on your bench, would you recognize it? And, because we don't have the test, the PCR test that we would use, for example, for life as we know, for chemistry as we know it. But, it seems that on this planet, that carbon-based life is the answer, is what evolved here. And that's kind of interesting, given that the Earth mantle, although carbon is ubiquitous and more common in the universe overall and in the galaxy, that there's more silicon than carbon in the Earth's mantle. And yet, life didn't take advantage of that resource. And I think it's because of the chemistry of carbon, which is just so much more flexible, forming single bonds, double bonds, triple bonds, long hydrocarbon chains. Carbon dioxide is a gas, which is easy for respiration, compared to silicon dioxide, which is sand that would get stuck in our lungs. So silicon-based life might be possible, but I don't know. Again, I'm going to bet on carbon-based life as yeah.
There's actually in early, like in 19th century science fiction, before you get the imagination of aliens as little green men, which doesn't come for much, much later in the kind of the history of alien representations, you actually get a lot more stories that are about crystalline aliens, like kind of crystal-based structure of aliens, and like rocks that are telepathic aliens. So there's a way in which actually looking back to some of the like older sci-fi before we had this very like dominant image of the humanoid kind of alien shows quite an abundance of imaginations about what life otherwise might look like.
Yep.
That is so cool. And we actually have an audience question that's really related to that, and science fiction sort of relationship with this field. They say, it's interesting to be reminded that the confirmation of exoplanets only dates back to the mid-90s, when planetary systems have clearly been important to science fiction imaginaries of life in the universe for much longer. We also see science fiction depictions of extraterrestrial life that are not planet-based, in nebulas or things like that. So they ask, what's the feedback loop like between science fiction and scientific exploration? And is there or will there be a search for non-planetary life? It's a big
I'm
one.
just going to say the science fiction writers are way ahead of us. I'm a huge science fiction fan, and it drives and spurs our imagination. What do you think, Lisa?
Whenever I interview people for my work, I always ask what they're reading, what they're watching, and it's of course always it's always science fiction. But I think I have thought about this question a lot when I was like writing and really deep in the exoplanet world, of like thinking like, all right, so Star Wars, those are all exoplanets, right? Like, Star Trek, like exoplanets were just so in the vernacular, and I always wondered about how that actually made it a little bit hard to explain how exciting those 1995 discoveries were, because it was just so common, like public vernacular, that of course there's other planets, because we have all these science fictional universes that are very realist, that are about the exploration of other planets. And I mean, that discovery was still a big deal, but I think that even today, when people hear about exoplanets astronomy, and Deborah, you might get this, I'm sure you get this a lot, they just kind of like, well, don't we already know this? So it's really, so I think you're totally right, which is the science is still catching up to the science fiction.
Yeah. Yes, I definitely get that question. And the other question I get from business people are, wait, what are the practical applications of your work? Like, how are you going to make money doing this? Yeah. You're waiting for me to answer that, aren't you?
No, I am a little bit curious. How do you answer that question typically? Or does it get into that maybe question of, why are we so passionate about this? Why do we all sort of inherently care so much about this question?
Well, I think like Lisa, this is something that I've actually thought about since the first time I was asked that question 25 years ago.
Mhm.
And I think that human beings, like, okay, we need to eat, we need to be safe, we need to, all of these things, but we also need like beauty and awe and wonder. And I think that's something that astronomy and science provides for people. Um, so, so I think it's incredibly enriching. And at the same time, I recognize that, astronomy is not the first thing we're going to do as a nation. And I think that our budget reflects that realistically. But I do think that it's important to a lot of people. It serves as an incredible hook for educating young kids who love astronomy and dinosaurs. And it serves as, the graduate students who are educated to become astronomers have among the most visionary, I think, education that I can imagine. Not only do they understand science and how data science works and careful, mathematical analysis, but we're driven by big questions that are visionary. How did the universe come into existence? How did every molecule in our bodies get here? Right? How do other planets form? I mean, these are questions that are incredible, and we have been able to find out the answers. I mean, yeah, I'm just like, I love science.
It's inspiring, absolutely. Lisa, what about in your work? What have you learned about sort of the history of these big questions and the motivation for this work?
Yeah, I mean, I tend to be attracted to science and endeavors where they're asking these big questions. So I am, and exoplanet astronomy did not disappoint. Like, I have all these beautiful quotes that I write about from graduate students, from professors, about the kind of beauty of what they're doing and the significance of what they're doing. Like, sometimes when I ask scientists or engineers not in exoplanet astronomy about like the significance of what they're doing, it's very bogged down by like the next step of a long chain of discovery or something. And that like just wasn't the case with exoplanet astronomers. When I would ask them like, why do you do what they do? They'd be like, well, isn't this the question that we've been asking since the dawn of time? It's like, well, I guess that's a good motivation. And so that got me really interested in trying to understand, like how do we trace the lineage of this question? And I was always really struck by the fact that in like exoplanet astronomy white papers, again, there's a real like self-awareness of the historical and philosophical implications of the work being done. That's actually like often a title in white papers, historical and philosophical implications. And those papers almost always like begin with a quote by Epicurus and kind of this Greek philosophizing that, there are millions of infinite planets, both like and unlike our own. That's kind of a concept or a quote that's trotted out and again in order to illustrate to a potential funder or to a member of the general public that the question that exoplanet astronomers are asking today is the same question that the ancient Greeks were asking. So as an anthropologist, I was really curious, like, okay, so even if like linguistically the questions are the same, is it conceptually the same? So I kind of did like a mini trace of this question of the abundance of other planets in the universe from the ancient Greeks to today. So, and I covered in about 3 pages in the book, so it goes by real fast. But, part of what I learned is that when the ancient Greeks were asking this question, they couldn't fathom having even a telescope to, see, to grasp at these worlds. Like they were, so when Epicurus asks the question, it's really a metaphysical question. He's trying to wonder, like, are we in an Aristotelian universe in which there's a prime mover, some kind of like, godlike figure that cares about what I as an individual do? Or are we in a more freewheeling universe, which of course the Epicureans want to think that they're, they want to be able to imbibe and, drink and party. And so they don't want to be bogged down by this prime mover. And so the question about other worlds was actually a justification about individual agency, right? If you have other worlds, then this prime mover can't exist because it would have to be in like all places at once, right? So that's kind of when Epicurus is asking that question, it was much more about this metaphysical question of who am I and who am I responsible to? When it gets asked again several centuries later by someone like Fontenelle in a conversation between multiple planets. I'm butchering the title of his book, but he's then asking this question in the wake of the Copernican revolution, when Earth was decentered as the center of the universe. The Aristotelian model was shattered, and the sun was at the center. And there was a sense when you read this kind of literature, the first time of translating Copernican ideas from the Latin into the English and into the French. In this case, it was the vernacular for Fontenelle. It was a sense of theology, of really treading lightly on this question of other worlds because of Copernicus and how he met his end with the church. So that's like kind of yet a different, it's not metaphysical and it's not quite the motivation of today. It's instead this much more theological question. So then what's the motivation of today, right? What are we talking about when we're talking about this question of are there other worlds? And I began really thinking about how to answer that question in as short of a time frame as possible. Like, what does that mean in like the 2010s? And I began thinking about how, particularly at a time when our media landscape has changed and there's all this disconnection, there's something really powerful about drawing new connections beyond our own planet to other solar systems. And there's something about what the science writer Dennis Overby called this idea of cosmic loneliness, that exoplanet kind of offers itself as solving. So I often think of the question of other worlds today as somehow this answer to loneliness, which I just think is so beautiful. And there's astronomers who I've interviewed with and have heard talk about who say that they have this profound sense of comfort if they can one day maybe be able to look up in the night sky, identify and point to a star and know that that star has a habitable planet, that's some kind of sense of comfort. And that's magical. I just absolutely love it.
That is, it's amazing. Absolutely. I guess one more media question before we maybe move into some more technical ones. Someone just asks, maybe based on these sort of big motivations and big questions and stuff, are you satisfied with the way that exoplanet astronomy is portrayed sort of in the media and to the public?
Sometimes. One of my favorite movies, I think I've watched it 150 times, is Contact with Jodie Foster. And I just think that is so well done. It's just mind blowing still to watch that film and think about the process of discovering extraterrestrial life and how it's going to uproot everything. And it's well done on just sort of every count. And then there are other science fiction movies that are maybe not, right. The science is off so much that it's hard to believe. But yeah, what do you think, Lisa? This is more of a anthropological question.
Well, Contact is my all-time absolute favorite space movie, and I often screen it for my undergrads because it's not a classic, and they haven't seen it. Probably the only students when I ask if they've seen Contact who raise their hand is because they've had a class with you. You encourage them to see it. But I think I was really interested in another change I saw in this kind of very recent period of exoplanet astronomy in the kind of press releases, the artistic images that accompany new discoveries. Because in the olden days of the early 2000s, those images were always of these, all that was really discovered were gas giants. And so the images were always these kind of Saturn or Jupiter looking gas giants. And I had interviewed a couple exoplanet artists about kind of who had worked in that period. And they kind of said that they weren't allowed to take too much creative license because they didn't want to be overreaching. But now, once the art moved in-house, because now JPL does a lot of the image work right in-house, it's these amazing quasi-photorealistic images of the surface. So I'm curious, Deborah, what you think about that as someone who kind of spanned these different artistic public imaginations. Does the realism of today and the view from the surface, does that make you nervous? Does that make you excited? How do you feel about that change?
No, I like the change. I think it makes it, but before there was almost a stamp. You can look at all of that space art and know that it came from, between 1995 and 2005. There, you're right. There was a very sort of stale and fixed way that exoplanets were depicted. And I see it as inspiring in the same way that science fiction is inspiring to have more realistic versions. And sometimes I think those just trigger our ideas about what research we want to do to see if that picture is right. What do we need to do to get that image? I mean, we have an image now of a black hole. Yeah. So, the exoplanets are not far behind.
Yeah, that's another really cool, like that relationship between science fiction and the research and art and imaging. There's a lot of sort of, cool feedback here.
It's very dynamic.
Mm-hmm. So we have a couple more audience questions about the potential for sort of common origins of life in different places. So one person asks, are you proponents of the Panspermia theory? And another comments that we've found amino acids in newly fallen meteorites. Do we think that those might be restricted to our solar system or are throughout the universe and are common building blocks? Curious to hear about your thoughts.
So in fact, since this is the Peabody Science Café, the Peabody Museum has a big chunk of the Murchison meteorite, which is a meteorite that landed in Australia and was recovered quickly so that there wasn't time for it to be contaminated. And in that meteorite, there were examples of not just amino acids, but also some nucleic acid bases, I think, cytosine or one of the bases was found. So that meteorite just brought us a chunk of chemistry from the solar system, right? This is a rock that was floating around, wandering around our solar system, and just happened to cross in front of Earth and get captured and land on the surface of our planet. We have lots of meteorites, and so we know what the chemistry of the solar system was like, but we also use telescopes to look at the spectra of other like cloud forming regions, star forming regions. And we see that the galaxy is literally glowing with the vibration of polycyclic aromatic hydrocarbons and precursors to amino acids. So the carbon-based chemistry is it's here, it's there, it's everywhere. Sounds like a Dr. Seuss book now, but it's raining down on other worlds, and I think that's why I think that carbon-based life is probably the way to go. So let's see, the question was the amino acids that we're finding and also about panspermia. Mm-hmm. But in terms of panspermia, the idea that life originated somewhere else and then came here, that our planet was seeded. Maybe, but I guess I would find that to be, and now I'm projecting, right, feelings, but I would find that to be disappointing if planets can't just, somehow the process that drives chemistry to become life, if that process doesn't happen spontaneously on worlds, then it's really limiting in terms of the diversity of life elsewhere. So I'm going to bet that life just gets started other places and that process is actually easier than panspermia, so seeding everything. And at the same time, admit that, I believe that we will be sending little nanobots to other worlds if we don't go there ourselves, and that those nanobots will contain the chemical molecules that they need and the instructions to assemble our DNA on other worlds. So that would be some version of panspermia. So it's possible that some combination of those two things happens. I'm not sure if I answered the question about the amino acids though.
No, absolutely. Yeah. The question was this contained to our solar system or potentially universal, which you definitely did. And I had no idea about that.
Yeah.
Mind blowing.
Yeah.
Lisa, do you have anything to add to that question?
I would just kind of reference once again contact and, bring up the concept of Occam's razor. And, all explanations is probably in the end going to be the easiest or the simplest that gets us these big, profound answers.
Right.
Well, so related to this idea of then sending life to other planets, someone asks sort of the interesting reverse question of the opposite of identifying life on other planets is, would we recognize or would we be able to interact with alien life if it came to our solar system or our planet? Any thoughts about how that might go down?
Yeah. Lisa, I mean, it's such a good question. It's so interesting, right? To think about whether we'll be able to communicate. And there are people who are working at the SETI Institute. SETI, of course, is the Search for Extraterrestrial Intelligence. And some of the things that they're doing, I mean, these researchers, like, these are not fringe scientists. These are super incredibly brilliant, creative scientists who are doing things like taking Fourier transforms of the vocalizations of whales and squirrels to figure out if, there are patterns in vocalizations, so that if we pick up some other signal, we'll recognize it as something that's intentional versus just random background noise, right? That's just amazing. So I don't know, it's hard to say if we'll be able to communicate with the aliens, but I kind of like to think that if they took the trouble to come here, that they'd have a plan for interacting with us.
That's totally how, I mean, I was thinking about the animal studies at SETI as well. Like, I was like, well, we're still trying to work on our dolphin communication. But yeah, I definitely feel like if I totally hope that we're not the most intelligent species in the universe. I definitely, I kind of want to put the onus on the others out there to, figure out how to communicate. We don't need to solve the problem ourselves. We can solve it in partnership with others.
Definitely, they got this.
Yeah, I have become, I think in terms of simple single-celled organisms, which invented themselves, which came into existence on our planet between 3.5 and 4 billion years ago. I mean, the Earth is 4.5 billion years old, and life sprung up on this planet relatively quickly. The life, of course, was anaerobic life. So because oxygen atmospheres hadn't been invented yet on Earth. And so those organisms, then those microbes mutated to take advantage of the energy of the sun into bacteria that are called cyanobacteria. And the cyanobacteria, as a byproduct of their metabolism, gave off oxygen and slowly began to titrate this more oxygen-rich atmosphere. It took from 3.5 billion years ago, though, when cyanobacteria invented photosynthesis, to just about 500 million years ago, right before the Cambrian explosion, for really sophisticated, complex, multi-celled organisms to spring up in this oxygen-rich atmosphere. So my guess is that, just thinking about the Earth as a prototype, that it was easy for simple organisms to get started here and to flourish here. And those anaerobes, microbes, will probably be here long after we are extinct. They have a very long lifetime. And so my guess is that those are common on other worlds as well. And that it just depends how Darwinian evolution proceeds as to whether there are opportunities for other life forms to spring up.
Thank you. That's so interesting to think about. I think we have time for 2 more questions, and we've got 2 kind of great ones from the audience. The first one is, are there efforts to estimate the number of possible habitable exoplanets? So maybe we can talk a little bit about the Drake equation or things like that.
Oh, yeah. Is this one of my students asking because this is their final exam question?
Oh no, maybe it's a plant.
Yes, there definitely are efforts ever since the Kepler mission that Lisa mentioned was launched and returned statistical information about the planet occurrence rates. Kepler did not quite reach a good measurement of Eta sub Earth, the number of Earth-like planets per star system. And that's because it lost 2 of its reaction wheels and had to be repurposed into a slightly different mission. And also because those planets are just hard to detect for a couple of reasons. But yes, there were a flurry of papers that have been based on the Kepler detections, which estimate the number of possible habitable exoplanets. But I would say that there are no like outstanding candidates of habitable worlds yet. We are right at the threshold. Like we have been pushing so hard. And I think that's an area where in the next decade, we can hopefully expect some progress.
Awesome. Lisa, anything to add, or should we move on to our final question?
Yeah, let's get the final question.
Okay, awesome. This one's kind of an overarching one. Basically, just if the current progression in this field continues, do you think we'll get a solid answer on whether aliens or other life forms exist? And if so, what kind of timeline do you picture for that happening?
I can go first with the anthropological answer there.
Perfect. That's
as a student of exoplanet astronomy, part of what one gets used to is kind of a constant deferral and moving of the goalposts. So probably when I was doing my field work in 2008 to 2010, everyone was saying, in this next decade, we will finally get to the habitable planet. And then, Deborah just moved the goalpost.
You just took my answer.
So yeah, I think that we're gonna be at a history of deferrals and kind of like thinking we get close, but then move. I mean, this happened with just like the quest for an Earth-like exoplanet, which is first it was just had to be like kind of the size of Earth, and we found a bunch of those, but that's not really an Earth-like exoplanet. Then it had to be in the habitable zone. Okay, well maybe we found some of those, but it can't be around a dwarf star. It has to be around a sun-like star. So it's kind of this. So what will it ever mean? First of all, to find the mirror Earth, like we can always change it, because then maybe we find one that's just like us in the habitable zone sustaining water, but there's no trees. So how could that be the mirror Earth? And then you keep looking. So I have my guess is that the search for alien life will proceed in our lifetimes along a similar trajectory.
Good. That's a great answer. And I would say I spent 4 years from 2016 to 2020 serving as a community co-chair for a NASA study to build a large telescope that was specifically designed with the primary mission of finding biosignatures on other rocky worlds. So I would say that if a mission like that gets selected, and we should know in a couple of months whether or not NASA is going to go in that direction, then in a time scale of a decade, sorry, Lisa, but I would say I actually wrote down 10 to 20 years, I think we'll have evidence for biosignatures on other worlds. Now, but the question is really about aliens. And I think that behind that word aliens is, sentient beings. And there is a possibility, just like in 1995, there was a possibility that other stars didn't have planets. There is still a possibility today that we, at this moment in time in our galaxy, are the only technological communicating civilization. I hope that's not true, but it's possible. And then as one of the attendees asked, would we be able to communicate with them? Are we on the same wavelength, or, how can we find them? So it's sure to be an incredibly exciting time for the next 10, 20, 30 years in this field.
Wow. I can't wait. I mean, that sounds amazing. I can't wait to see what happens next. Do either of you have any final thoughts you want to leave our audience with today?
I love the final thought of just how exciting the field of exoplanet astronomy is, and how it's only at the beginning. Like there's going to just be so much that's going to be learned. And it was so exciting for me to be there at like really the beginning. And now I just love seeing the field progress.
Yeah, I think for me, it's that the rate of discovery has been just booming and exponential. I mean, from the time that the first exoplanet was found in 1995 to now, to go from, 0 to, let's say, call it 5,000 exoplanets, and to be able to characterize them and see their atmospheres and figure out if there are winds on the surface of the planets. It's just astonishing, I think, how clever scientists, astronomers can be in this field. And as long as we continue to get new instruments, we will continue to have new windows on the universe where new things will be discovered.
it's so exciting to think about the future of where this imagination and instrumentation and discovery could go. So I think we'll go ahead and wrap up. But first of all, I just want to say thank you so much to you both. This has been so interesting. I hope our audience has had a great time. There were a lot of really great questions. So thank you as well to the audience. Thank you for being with us here tonight. I want to say a quick thanks to the Peabody staff that have been helping plan this and run it behind the scenes. And if you're interested in hearing about more events like this one, feel free to sign up for the Peabody email list or follow the Peabody Museum on social media. So with that, I hope you all have a lovely evening and thanks for being here.
Thanks. This was so much fun.
Uh-huh.
Thank you.
Bye-bye.